Hello, everybody, and welcome to Handmade Hero, the show where we code a complete game live on stream. We have to do some thinking today about how we want to proceed with our lighting. Now that things are actually working in the OpenGL driver, and we sort of have the nice luxury of actually being able to debug our graphics card stuff now, and it can even crash, and we can still stream because we're now on two separate machines, one for streaming and one for programming. And one of the things that happens, it's not too infrequent actually, when you have to do sort of graphics code that's a little unusual or does anything that could be a little squirrely, you often will crash your graphics driver. That's just something that can happen. And so it's pretty nice now not to have to worry about that. We can just crash the graphics driver all we want, and it's no big deal. So when we left off yesterday, let me get this running here. When we left off yesterday, we were kind of playing around with the way these things kind of get set into voxels, and as you can see, we ended up in a position where we now can play around with the lighting and try to figure out how we're gonna get these sort of voxel-based samples in there. We sort of have two separate problems that we need to address. And also, I should mention that I think I was kind of sitting around thinking about some stuff that I was wondering about some depth occlusion stuff today, actually. I think last night as I was falling asleep, I was thinking about it. And after this, I would also like to revisit how we're doing 2D sprite compositing into the 3D world, because I thought of some things that we didn't try there, and I would be interested in trying them at some point. So I have to remember to do that, just put a little mental to do in there, like something I wanted to think about a little bit more, just kind of work through it a little bit differently than we had been, but that's neither here nor there. Anyway, so the situation as it stands right now is we backed off. We kind of like went down to a coarser grain thing and sort of took a look at what that would look like if we had smaller and smaller voxels, just so we could sort of see what the difference was with various lighting, different lightings we could use. And the way that we're storing things right now is we have a voxel lookup that allows any pixel that wants to try to figure out what its lighting value would be to go ahead and calculate the lighting, if it wants to, from any number of sources based on a linked list that's in voxels that it can look up into based on its position. So any particular point in here, right, there's a voxel, and you can see it because we now have sort of chunked lighting in here. There's a voxel at each sort of position that's about, sort of a square this big, and it's a fairly elongated because there's less of them in Z, so they're elongated in Z. And what you do is, wherever you are in the voxel, you can look up and get a linked list of computed reflection points, like basically points where the lighting has been computed, that you can interpolate between. And the problem that we're going to have with this, obviously we have some work to do to try and make this work cleanly, but the problem that we're going to have with this is, as we want to interpolate the lighting, we're going to have problems where we have to make sure that our voxel is about the same density as the lighting samples that we've put into it. Hopefully the lighting samples actually are a little more dense than the voxel itself, so that when things are interpolating, they can always have some points to interpolate between. Now, the first thing I want to do today before we get any further into this is just try doing a basic trilinear blend. So for any given pixel, wherever it is, it'll do the lighting on essentially like the same way that we would sample a texture, if you will, or something like this, where we blend between the lighting sample, the computed lighting sample values in each of the 4 voxels, or something like this, right? And I guess what I should do first is kind of go over what the problems are that we're going to have, why this is a bit of a tricky situation that's going to require some finesse to try and get right, and so on and so forth. So here we are on day 409. By the way, is there a way to get Milton to not have a title bar or anything? Probably not. I was going to say we have the sort of nice four-coder when we load up the code here. We have the sort of nice no title bar thing. I leave the file bar up for people because they asked for it, but normally on my dev machine I get rid of that too. So you get this sort of just nice screen of just the code. It would be kind of neat for Milton to get rid of its title bar too, because then you could have like nothing, right? It'd just be a big blackboard. But that's kind of a minor thing. I should just go do it myself. The source code's available. Send a pull request. Anyway, on day 409, what I wanted to talk about here is the light interpolation. And so the problem that we have with light interpolation is we have the idea, and I'll draw sort of a voxel trilinear case here so that we can sort of work towards that. We have a voxel, and we've got somewhere in this voxel, we have a pixel that we're trying to light on the screen, right? And so what it knows is it knows where in the voxel it lands. So it knows, for example, that it's in this cube of the voxel. Well, it's not really a cube because it's I think the z direction is less sampled. I don't remember exactly how we left it set up, but point is it's probably not a cube. It's more like it's a right rectangular prism of some kind. So anyway, we have this place where we want to compute the lighting, and we know that it's inside a particular cube of the voxel or right rectangular prism, as the case may be. And what we want to do is we want to then take some measure of the lighting we've computed and apply it to this pixel that we're trying to light. Now, all we have inside this voxel rather is a linked list, right? So we've got a linked list of lighting samples, and the lighting samples have like a position and a color, right? So they sort of say, well, you know, I was over here and I was this color, or I was over here and I was this color, or whatever. And so there's a lot of different ways that we can try to work with this, right? So let's start with the simplest possible thing we could do, and the one that would be the cleanest to implement and easiest, right? And who knows, maybe it's even like what we should do. I mean, it could be that it's fine, but it has some drawbacks, and I'll say what they are in a second. So one thing we could do is say, well, just forget it. Like, don't bother storing this information at all. Let's just store whatever the average color value was, right? And then just use that as the lighting. Done, right? If we did that, so each voxel position, just all the voxel had in it was knowledge of what its color value should be light-wise. Then in each of these locations, I would have one color. And so I could just take, using trilinear interpolation on these 8 samples, I could just take whatever the location of the pixel being filled was and know what its lighting contribution, what kind of light it was receiving, strictly based on that, right? That would be all I would need to do. And so that's one thing that we could do. And if we were going to do that, then what we would do is rather than compute what the reflected light was at those points, we'd just record the incident light at those points during our lighting pass. And that's what we would store here. So we know that the generalized amount of incident light at this point is blah. Now, we chose to do something a little bit better than that in terms of what we store. Excuse me. Which is that inside here, what we actually store is a position and a color, which is to say that we have multiple pieces of information about where inside this voxel our samples were taken, so that if we, for example, took one thing on this side of the voxel and one thing on this side of the voxel, then we could use interpolation within the voxel itself without looking outside the voxel to actually give more information about how color varies over the voxel interior to its own volume. We could actually vary it based on information strictly related to this voxel without even ever looking outside the voxel, which gives us even more information, right? And so the problem with that is that once we have a particular piece of information regarding what happens inside the voxel, we now no longer really have any way to figure out what we would do about when we get to the edges of the voxel, right? Because let's take the simpler case to draw where we were doing this as bilinear interpolation, because the problem exists in any dimension. It doesn't matter whether you're in 1D, 2D, 3D, etc. So if I'm in 2 dimensions and I have exactly the same scenario, then what I was proposing as the first and easy solution is if we pretend that there is an incident light value at the center of each of the squares in my quadrilateral here for bilinear interpolation, and I've got a particular pixel I want to fill, then it's a simple case of bilinear interpolation, as we said before, to figure out what the color, or in this case incident light, should be at this point. Because bilinear interpolation is very straightforward, and we know that it will be continuous, right? When I get to here, I will be set up to be exactly on this line, so that when I continue across and try to figure out pixels over here or whatever, it will be continuous the entire way, right? It's always blending between 2 things, and when it gets to the one of them, it's exactly at that one, and then starts blending towards the other one. So there's no discontinuities in the blending at like boundaries where something like bad, where you'll get like an edgy artifact you don't like, right? So the next question is, well, what about, sort of the fancier approach, or the more detailed approach, where we store multiple lighting samples per voxel in a linked list like we're doing. So in the 2D case, what that would end up looking like is, rather than having things at the center, you might still have some things at the center, who knows where you have them, but you have something more like this, where there's sort of a scatter shot, right, amount of stuff in here, and there's no real rhyme or reason to where it necessarily is, right? It could be anywhere inside here. We don't really know. And so the problem with this becomes, when I have someone, let's say I take roughly the same position, I want to compute this pixel and what its color value is, and I don't really know how to do that because I don't have any way to do bilinear interpolation on it, right? So what I need to do instead is I need to have some way of interpolating various scattered sample points. And what I did, just threw in really quickly, was essentially a radial fall off. So that what I did is I took, the distance from each sample to the place we were trying to sample, and I let the contribution of each one fall off as it gets further away. Now, that actually works just fine. A radial fall-off weighted contribution like we did is a totally fine way of summing up points, certainly. But the problem with it is that it doesn't actually help you avoid the discontinuities that will happen once certain points fall out of your sample set. And the reason for that is because, let's say we end up sampling pixels along a line here, and our range of fetching is 1 voxel to either side. Well, I'm going to actually weight the contribution of this point right up till I get to this voxel boundary. And then as soon as I cross the voxel boundary, I will no longer consider this point. Which means that at the point when it would have fallen out, I had better have driven its contribution to 0. But I didn't do that, right? I didn't have any guarantee that a sample's radius was confined. So what we probably would need to do if we wanted to make that work is we'd need to force, if we weren't going to do anything fancier in this scheme, we would need to make it so that each individual lighting sample had a fall off that was no more than a voxel and a half, basically, right? Or 1 voxel, depending on how tightly we wanted them controlled. We would need to make sure that when you're fetching voxels from neighbor voxel boundaries, you don't consider any voxel that could fall out as you cross into the next boundary. So basically, if you imagine that a voxel, the furthest possible voxel and the closest possible voxel, right, let's do this. So imagine the closest possible voxel is right here on the corner, right? And what's going to happen is as soon as I cross out of here, right? As I'm sampling in this direction, as I'm stepping through pixels this way, let's say, this voxel right here had better not have a radius that can extend out into here, right? Because if it did, then its contribution would be non-zero, some actual non-zero real value right at the edge, and then as soon as it crosses over, it would become instantaneously zero. So rather than having a fall off that looks, you know, like this or something, it's going to have a fall off that looks like that, right? And that you will perceive as a discontinuity in the lighting. Very, very obvious one, right? So that is kind of what we're trying to deal with here, right? Is making sure that we would have some kind of a blending scheme that isn't going to have that problem. And I think that, so the easiest thing we can do to fix it right now, to just try and move it to something a little more sane, is to make sure that the radius, we take whatever the smallest radius is in our voxel dimension, and we just make sure that things can't contribute past that, right? So that they're never going to have more than one of those radii. So we can see what kind of a difference that makes. We don't really know whether our code is bug-free yet because we haven't really spent much time playing with it. So we don't know if there's other problems in here as well, but you can see that there's very clear voxel boundary problems, right? You can see we're not drawing those voxel boundaries. That's just lighting discontinuity that you're seeing there, right? So we can take a look to see what would happen if we changed our shaders to have that property. So when we compute the Z-bias program, I'm sorry, when we compute the lighting in the Z-bias program, if we wanted to make sure that that lighting would not pose a problem, then what we can do is in here we have the inverse cell dimension and the voxel min corner. What we could do is figure out a useful way of talking about distance that was sort of mapped into the voxel to begin with. And I guess what we could do is multiply by the voxel inverse cell dim before we compute the distance, for example, would be one way to do that. So when we do this subtraction, for example, here we've come up with a distance. What we could do here is say, all right, what we want to do is multiply this by the voxel inverse cell dimension. So now we know that all of these distances are going to effectively be expanded or contracted properly so that a distance of 1 in any direction of the voxel is going to mean we went one whole voxel's worth of space, right? Then when we do our clamping to make sure we clamp between 0 and 1, in theory, I think that would do it. Now, unfortunately, we're not square, right? So I don't really know if that's okay. That's a very interesting. That's a very interesting color pattern. So what I will say about that is it did sort of do what I wanted to do, which is it avoids the discontinuity. Unfortunately, it creates a very weird effect. So I'm not sure we really want to do that quite that way, but it's kind of interesting. That is very, look at that. That's very odd. So maybe that's not the best idea. I have to think this through a little bit of whether that's even really the correct way to do it. But point being, we can also test it slightly differently here. We can do, when we do our length squared, we could say, well, whatever the voxel size is supposed to be, we can, whatever the smallest voxel size is, we can go ahead and make sure that we don't blend at any further than that, right? And so the way that we would do that is we just say, well, the distance squared function that we're going to come in here when we take the length squared of this, when we take the length squared of the delta, we can just divide that by the max distance squared, right? And that'll make sure that that will be, or we can even just make a coefficient so we don't have to do a divide. Obviously, we could just do something here. We do dist norm constant, right? So we just have to compute some value that whenever we get a length squared, that length squared is going to be some arbitrary value, right? It can be arbitrarily far, so it doesn't have to be something that's just a voxel size, right? And so what we want to do here is say, well, okay, we want to make sure that we force the value to be clamped at a particular position. I guess, the other thing we could do here too is we could adjust this value as well. In fact, I guess that's really all we have to do. After we compute the length squared, we're going to take our sort of value, and that's the maximum distance. Really all we have to do is this, because this is already our maximum distance here, right? So our max blend distance is then going to get subtracted by the distance squared. In this case, if we wanted to keep it squared, we'd have to square it. So really, it'd be that. But subtracting two squareds really isn't something you can quite do that way. So if we really wanted to be accurate about this, we would probably also want to square root the distance. I'm not sure how sane that is in terms of performance, but it's probably not too expensive in shaders these days. Probably just 4 instructions or something like that. Maybe even less. Maybe just 2. Anyway, so when we do a max blend distance here, what we could do is square root the distance squared, something like this. And actually get an accurate fall off that's based on a linearized radius as well. And again, I don't really know to what extent we want to do that or not, but we can. I should probably put in something like that to keep it the same as our other code. So that just leaves us with the problem of having to pass max blend distance in. Again, max blend distance in this case is just the maximum side of a voxel. The problem is we don't actually know what the maximum side of a voxel is because we're only past the inverse cell dimension. Now what we can do is invert it and get that, right? We'd rather just pass it in, but we can if we need to. We could actually pass that value, right? Or figure it out. Because we know that the max blend distance is just going to be the minimum value, right? And did I define a min? I didn't do that either. Oh well. It's just going to be the minimum value, which I believe we can just use min, of whatever the inverse cell dims are. So each of these inverse cell dims, if we were to just invert them like so, right, and get back the actual cell dimension, then we would just take whichever the minimum was, and that's how far we want to go. Now, in our case, there's no point in doing this divide 3 times and then taking the minimum, because we know that whatever the maximum value is will produce the minimum value here. So what we could do is just say 1 over the maximum value of the cell dims themselves. Right? So that way, it's like whatever your highest number is, we'll do 1 over that, and that will give us our lowest number, and that would be the maximum blend distance. There's no sense in doing this math over and over again every pixel, so this is really something that should just happen and be passed down. But, right now I'm just kind of hacking it in there to see whether it's something we care about at all. Oops. It's Vox im cell dim. Yeah. So anyway, excuse me. what you can sort of see happening here is this has roughly done exactly what I wanted to do, I guess you could say. So if you look at what's happening here, we're getting kind of exactly what I would have wanted to have happen, which is that we are keeping everything constrained to about 1 voxel size, and there's no discontinuities. So I really can't complain about that. That's basically what I wanted. The problem, of course, as you can see, is that the samples are so sparse that there aren't even samples in some of these voxels, right? There aren't even samples at a lot of these voxel locations. And so as a result, what happens is when we try to blend together, we just get nothing. So, you know, there's nothing in this voxel right here, for example. And it creates just a little pools of contribution with nothing to blend them to, right? And if you're wondering why they don't blend out to 0, the reason is because we normalize the lighting, right? We're blending together only insofar as there are multiple samples. We don't include nothing as a valid sample in the current state because we really don't ever want to be in that position. So again, you know, what we can do here, of course, is we can drop the size of the voxel down to something very low. And that allows us to always have enough samples, but then we start having this problem also of the voxel not really doing much work for us. And so we kind of have to sort of think about how we're going to do something a little bit more sane with that, right? But let me go ahead and here we go. So now this is with the voxel dimension dropped very low. And you can sort of see that with how low the voxel dimension has been dropped, you can sort of see that now we always have multiple lighting samples everywhere in the scene, right? And I guess like it's kind of hard to tell whether this is a particularly good interpolation of those samples, however, because one of the problems we have right now that we probably would have to fix is just not like we have to have some method whereby we could visualize where our samples are, so we can toggle between that, you know, in some kind of relatively clean way. Because you see, you get a lot of these sort of bubbly effects here, and that's actually just, you know, I don't know that that's necessarily anything buggy, because that's probably what you would expect to see in the circumstance where you had a radial basis sort of a radial fall off for how you were summing things together, right? That's not that strange. That makes sense. So yeah, so we kind of just need to figure out some ways here that we're going to be able to, again, to get around that. So a couple different things we could do. Like I said before, we could just try to do lighting computation at the voxel boundaries themselves, right? So that we always try to do stuff that, you know, ends up creating an incident light value at individual voxels. And then we trilinear interpolate between those. That's a totally sane way to try and go about it, you know? I'm not sure whether that's a sane... I'm not sure how sane that is specifically. I will say that, yeah, it's sort of working okay. I mean, you know, it's not that far from a usable solution at this point, which is kind of nice. Like, it sort of does work in terms of, you know, when I'm down here and I recompute the lighting and this light is here, like it kind of does look like it's roughly confined to that or whatever, right? So that's not bad. But yeah. But anyway, but we're still pretty far away from having something that I really consider good. So yeah, anyway. So the question is just how do we move forward from that? And I'm not sure, right? I'm not sure exactly what the easiest way to go forward from that is. Whether I should try to figure out a good way to integrate these samples together and still keep multiple samples for voxel, or whether I should assume that we're just going to compute lighting in the voxel itself and let everyone try to compute their lighting from that. Yeah, and I don't really know. So there's a couple things here. The first thing that I'd like to take a look at is we may be kind of doubly contributing here. Because we record the lighting values at these locations, and then we also multiply by the lighting values at these locations, I'm kind of interested to know what happens if I just use the lighting sums directly. I'm just curious. Okay, so we are not storing the lighting pre-multiplied by the surface. We are just storing the light value. So that's good. That means that our colors are not sort of getting double weighted, right? Which is what we want. Good. So this remains a valid calculation, and I am happy about that. So I guess my next question is, if we were to do some denser lighting sampling, we're computing lighting at all of the vertices. And I guess I'm not really sure why we get some of the patterns we get there, though. Well, actually, that does look kind of accurate because we're moving little tiny lights around. One of the problems we have is our lighting computation itself has not been GPU accelerated yet, so I can only take it periodically, which means we can't see really how it moves, you know? And that affects the interpolation, obviously, like whether the interpolation would look good in motion, we don't really know either. But one thing that's definitely true is we're just not getting a lot of bounce either. Like, you know, the lighting here doesn't really flood in much in the way that we might want it to either, which is not perhaps the best thing in the world. And you can see that these patterns are kind of weird. They don't make a huge amount of sense to me. I'm assuming that's because of the way the fall off is written right now. When things kind of combine together, there's probably a little bit of a weirdness there. So I'd like to look at the samples again, if possible. Or perhaps even just adjust the samples. So let's suppose that we were going to do something a little bit more squinky there, where inside the like voxel, let's try to make the voxel still be relatively large. And so I believe, you know, this is roughly just looking at the lighting samples, right? Like this is more or less telling us exactly where our lighting samples were, I think. I don't know that that's necessarily true, but I think that's true. And so, you know, the lighting samples are getting placed sort of at these 4 points on a cube, right? And so, you know, what you'd want to do here is you want to just kind of look up the ones that are related to you. I mean, you really just want to fill between these, for example, in these cases, right? I mean, what you really want is to just kind of say, well, all right, I've got these, and let me just kind of fill those in. But the tough part, right, comes when, you know, you want to do sort of these corners here. You want this to kind of fill down to this light here, and I don't know. It's kind of tricky. So figuring out how to like gather these back up is a kind of nasty problem, which is not surprising. There's a lot of papers written on this sort of thing for lighting gather kinds of filtering to try and figure out, you know, from multiple lighting samples what the lighting value at some new point should be is actually, you know, it's not easy, obviously. But and I guess I'm not really sure to be honest. So I guess I see what's happening here. So these are bright because there's these yellow lights that are here, and they're lighting up the red. And these are bright from this guy. So that's why you kind of have these two bands there. So that's all right. Yeah. So here's what I'll say. Looking at this, right, it is still the case that these lookups just aren't great, right? Because let's suppose you outputted a scene that looks like this. I would argue that actually this is probably dense enough of a lighting computation to be okay. You know? I mean, I would say that that's a totally reasonable amount of lighting to be able to interpolate between to get some kind of a relative idea of what the color of the surface should be. And so the voxel lookup scheme just isn't really sufficient here. Like, what you really want to be able to do is sort of more of a give me a few of my closest points. And that's not necessarily what the voxel is going to be good at, is the only problem. Because the voxel is always a fixed size. You know? The voxel is always a fixed size. And so there's not much it can really do about that. You know, it's not going to be able to really adjust. So you kind of want there to be more of a, I guess almost more of a flood fill kind of a thing. Like if you were going to use a voxel, you kind of want all of the voxel cells to eventually get pointers into them that tell you, you know, other points, where the closest points are. And at that point, it really does seem like you just want to compute coloring for each voxel in some other way. Yeah, so I don't know. So I'm kind of leaning towards saying, you know, we probably want to do some kind of pre-processing on the voxel there and maybe send something down for the voxel where the voxel is kind of more of a just each voxel cell says a rough irradiant direction. And the reason that I'm a little hesitant about that is just because you get into situations where you have a single voxel cell that has more than one, like, primary piece of information in it that's important, you know? So in that case, having, the linked list, I was kind of thinking would be the way to get around that problem. But I'm just afraid that storing these things in the linked list maybe isn't the best idea. I don't know. I'm kind of interested to know what a non-gradient wash version would look like. I want to know also where, if we flood fill with closest point, basically, what that looks like. So rather than doing, a light sum like we're doing, if we just picked the closest point, I wonder what that'd be like. I also don't like how many voxels we have to look in. There's just a lot of them. And that doesn't seem good either. So I think what I may do, let's start with sort of something simple, which is let's start by just summing 8 voxels total. And we'll go from there. So in other words, we're going to start by doing something that's like this sort of thing. Let's just get this down to a more manageable number. 1, 2, 3, 4, 5, 6, 7, 8. So if we sum the voxel lighting, let's assume that we're going to compute a voxel that's like our base voxel, and we're going to go up 1 in each direction, right? But not back 1. So we will do, this sort of a thing. And let's assume that what we'll do there is we'll look to see which voxel we're talking about when we produce our voxel I. So if you imagine that this were the voxel just taken in cross-section there, what we want to do is say, well, okay, actually let me do it this way. Before, what we were doing is, let's say, gathering all of these. Let's start by just saying, well, okay, we're only going to gather, let's take the center point of a voxel and say, if you're if you're on this side of it, right, then we're going to use these voxels. But if you're on this side of it, then we're going to use these voxels. You know what I'm saying? So basically, break it up so that we're talking about like the center, wherever the point is that we're looking at. We're going to go back to the like half voxel boundary and use the voxels that make sense for that particular interpolant, right? And another way to say that, and perhaps an easier way to envision it as well, is if we just said, well, okay, maybe we just go ahead and say that voxels are sampled at their corner and are inserted into on their corner. So on the insertion side, we could do it that way. That way, we're always just taking that way this math is actually already correct. Because whatever the floor is, if the samples were here, 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 and here, then whatever the floor is already, you're in this voxel, so now you already know you're interpolating between those 4 points correctly. And that's where you should be. Right. So basically what we could do is that, I don't know if we really want to. We don't have to do it that way. What we would do is just increment by a half voxel before flooring, and we would get the same answer. So we could just do it so that things are still voxel based. I don't know. But there's not much of a difference there either way. We just have to make sure that we insert you can see that the lights are kind of clipped now. We just have to make sure that we insert the lights on the half boundary or look up on the half boundary. Since I kind of want the voxel dimensions in here anyway, I think I'm just going to say let's start passing those down, and then we can use them. Uniforms don't cost a whole lot to have, so I think I'm just going to say let's have the cell dim in here as well. And that way, when I go to do the flooring, excuse me. Well, actually, you know what? I still don't really need it though. I'm kind of trying to find an excuse to have the cell dim in there, but I don't really need it. Because since I multiply by the inverse dim, I can just add 0.5 at that point, right, before the flooring. So before I floor the point to find out which ones I'm going to look towards, I could just do, you know, that, right? And that makes sure that I'm going to be in the right, based on voxel centers, I would be in the right region. So, but yeah, again, that's not really going to help us too terribly much until we have something a little more sane to use there. Because if we don't actually do light samples at the centers of each of our voxels, then we, would have a problem. So let's try, though, just putting light samples at the centers of the voxels. I mean, it seems reasonable enough. There's not that many of them even at the moment, even if we did them all. But what I could do first is just say any voxel that actually is sort of in the region of something, we could put something in and do a lighting computation there so we don't have to have quite so many. But yeah, so all I was trying to say here was if we wanted to make it so that we're based off centers of voxels so that we know that, like, if there was a lighting sample at the center of each voxel and we wanted to go within them, just adding the 0.5 keeps the flooring value so that as I get up to here, I would actually move forward. So let me just make sure I'm doing this right. So normally when we floor, right, it's going to keep us inside this voxel for anywhere inside the voxel, right? So the voxels are going to be this one, are going to be these. You know what? Now I think about it, it's actually subtracting 0.5 is the way that I actually was drawing it, though. So it's not actually adding 0.5. I've got it going the wrong way. Because what I said I wanted to have happen was that if I was in here, I wanted it to be these, which means this voxel, this voxel, this voxel, and this voxel. If I went here, I wanted it to be these. So I actually want to subtract 0.5 beforehand, not add 0.5. That's actually what I would want to do to make sure that I have the voxels that I wanted. Because I'm actually going backwards, not forwards, right? Oh, it didn't like that at all. What did I do? That's a bit strange. Why didn't it... Huh. I'm not sure why it thought everything was out in the other case. That's a little bit weird. But anyway, this is the case where that I was discussing where it would pick the right voxels for blending the center points of those voxels. So yeah, if we want to do something like this, the key here would be we need to make sure that each voxel, though, does have something there in order to bilinear between them. And if we wanted to then bilinear, instead of doing it, we could write the bilinear code right now. So, you know, the light sum or whatever would just change to being something where it would normalize itself after the fact. So, for example, if we wanted to do that here, what we could do is something like this, where excuse me. When we go to sum the voxel lighting up, we do the sort of blending inside here, and we'll figure out, you know, at some point how that's supposed to work. But we would maybe figure out the blending based on the centroid of the voxel as well, if that makes sense. Like we would probably want to... We would probably want to compute the lighting value at the centroid of the voxel and blend between those. It's kind of hard to say. Well, let's keep going with this here. This is a bit wonky, but I'm going to do it anyway. So anyway, we have our result value here. You can see us computing it. And what I want to do is at the end, I want to normalize the result value. So I'm just going to say if the result value had anything at all, then I'm going to take the result value RGB and multiply it by the result value A over, you know, sorry, 1 over the result value A to normalize it so that now, no matter how many things we weighted together, we will always end up with an even weight. I'll get rid of this stuff. And then we just need to actually use it down here still, so this still wants to be, excuse me, I'll use light C. And so in here, when we get these voxel values back, like these are going to be a little bit more complicated now. So these are like, each of these is going to be a light value. We don't need an alpha value because we wouldn't really be using alpha anymore. So we'd really just be returning just the RGB value. What we'd want to do here is say, okay, we're going to capture each of these separately. Right, this would be us capturing each voxel value that we could get. So this computes the 8 voxels that are in our neighborhood, what their lighting contribution is. And then we can lerp between them, right? I think we defined our own lerp that has the order that I like, right? Didn't we? Yes. So we can do, based on the fractional amount of z, you know, we can do each one of these. And all I'm going to do here, right, all I'm doing is taking the various voxel pieces and doing lerps along them, along the edges. So those lerps, that would take z out of the equation because now we've got basically, we've taken our cube and we've lerped all of the z lines so that now we just have a square. Then we would do the same thing. It's just successive. Right, so take z out of the equation. Now we're taking, oops, y out of the equation. And done. So I hope you can see kind of what I was doing there. I'm just saying, like, all right, look, we need to do a trilinear interpolation. So first, let's produce a bilinear interpolation from the trilinear interpolation by taking the z-coordinate fractional bit, which I need to actually produce here. Oops. So if I take the Vox position, do the floor of it, like so, and also have a Vox F. Like so, this is basically saying what's the fractional amount that's left over, so we can interpolate by that. So we take the points of our cube and we say, all right, each one of those, we're going to take the z spans on the cube and lerp between those to produce a square, right? Then we're going to take those and to produce a line, and then we're going to take that to produce our point. And that's it. 122, huh? Unexpected opening brace. You did not expect my opening brace? Well, why didn't you expect my opening brace? Oh, I see. So here's the while loop did not have the brace in there. There we go. So that does not look like I did that right, however, because that should have produced a more bilinearly blended result, which it doesn't. Oh, I know why. Because it's still also, this is not actually, yeah, this is not just blurring these together. It's still doing the contribution based on the distance. So what I want to do here is just sort of smack these together and pretend that each voxel has sort of a constant illumination at it. So in order to do something like that, again, yeah, I can get rid of a lot of this code temporarily and just say like, okay, when we go through here and we look at the light values rather than having the contribution amount, let's just blend them together directly like that. There we go. So that still doesn't look right to me because now we should be properly handling the case. Well, properly handling the case is a little bit wrong, but we should blend to 0 in case, like we should be seeing an actual even blend. So let's debug this and get this down to the point where we don't see errors like that yet. Because if we take a look at what's happening here, if we've eliminated the position of, like if we eliminated world P, right? Because you can see world P now no longer appears anywhere in the sum code. So since world P is no longer in here, we expect some voxel light should return the same lighting value regardless of what who calls it, right? No matter when you ask, as long as you ask for a particular voxel's lighting value, you should get the same thing out. You should never get a different value out than for two different pixels that you're trying to sample. You should always get the same one out. So when we call it here, when we produce whatever the voxel fractional amount is, we should be able to do stable bilinear so that you always get predictable values as you go through, right? So that tells me that I'm not quite doing this blend properly, I believe. And so we need to figure out why. So first off, when we do our Vox P here, I believe that that looks like it would produce the correct value. We're starting at the -0.5 for the range there in terms of producing the flooring value, which seems correct. And once we produce a floored value, so this is backwards. We actually want to subtract the floor from the p-value to give us the fractional amount is positive, not negative. So that would have been a big problem there. Let me just check the rest of it here. The Vox index is just being produced from turning that into an integer, which it already is because it's been floored, so it's just converting from float to int. We're then summing the voxel lights in each of those locations, which again, now if we stuck with exactly this scheme, we wouldn't even need to store linked lists anymore. We'd just put the lighting values directly in the voxel. Although we might still want linked lists to keep the voxel sparse if we store a lot of lighting data in there. But that's separate. Okay, so that's more correct. Like that looks more like what I would expect to see. And looking through here, right, you can kind of see now, we always have a stable bilinearly filtered lighting no matter where we are, right? So that all looks about right. Again, the problem with that, of course, is that we don't really get, if we were to try and use this scheme as the way we were interpolating our lighting, we of course end up in the problem again of this light map resolution is just not particularly high, and it's regular, and we have to figure out some way to make sure we always get samples at the voxels, and so on and so forth, right? But I just wanted to sort of get what that would look like. So I think that is roughly what we would want to do anyway in terms of figuring out how we're going to interpolate, though I think we only want to look at 8 voxels at a time. Looking at 16 just seems too much. That just seems like way too much. Actually, it was more than that. It's 27, right? How many was it? We did all permutations, so we did, yeah, we did 3 times 3 times 3. It was 27. So I think we want to keep it to something like that, but whether or not we want to still try and use more information about where those lighting samples are, I'm still up in the air about that, because I feel like, I don't know, that still might be kind of necessary. So what we could do in this case is, yeah, I mean, we could still try to do something where we're lerping between these values, but we still make the values be, we could still use the lighting information in computing. So we basically say, okay, what would the lighting be if I was in this voxel? Okay, what would the lighting be if I was in this voxel? What would the lighting be if I was in this voxel, right? We still could interpolate that. If we were so inclined. I don't know that we are, but we could. And so what we could do is this, if we make this, in theory, we could make this still take that into account. I mean, that is still possible. So if we wanted to, we could still do it. I think the old school way, if we wanted to, and it would not really pose a problem, right? So we could still say, okay, compute a contribution here, and that contribution in theory could be anything you want, I think. So because since we're doing the bilinear, it will always properly fade at that point on the way out. So I think you could compute the contribution any way you wanted, probably. I mean, don't quote me on that, but that seems like correct. So if you wanted to take the contribution of something and say that it's whatever the length was, and then oops, and you know, we could even say just, I don't know, 1 over the length. I think we can make up any value we want here, and you know, who knows, we'd have to actually go try to think about what the correct value, what the correct weighting would be. But in theory, you should just be able to just do whatever you want, and then the bilinear takes care of the fact that you are computing it differently in different areas, so you don't actually get any discontinuities, and that does appear to be the case, right? So at that point, we really just have a lighting sample problem. And I don't know, again, like, yeah, so we could take a look one more time at what happens if we just force a lot of samples into the same place. Let's keep the Z sampling up a bit, because I feel like, you know what, why do I keep changing this? I don't even know why. We don't even really need this right now. This is not necessary. Let's just get rid of that. That's a little bit odd. I'm not sure exactly what we're seeing there. I think that's just our blend amount not being particularly smart. So maybe that 1 over is not really great. Let's try and fuss with that a little bit. So let's say our contribution is gonna still be 1 minus the length. that might be a little more sane. I should really think a little harder about what we want to do for blending, because I'm kind of just ad hoc here. That looks a little nasty. Why are we getting... And I guess we don't really... we don't really need to renormalize unless we're over 1 would be the other weird thing. Like, we could do this as well. Right? Which is kind of even weirder. That fall off seems a little too stiff as well, potentially. I don't know. Like, maybe it should be something more, you know, where lights have a bigger radius than 1. Just making stuff up. But something like that starts to look pretty reasonable, right? You know, it's not going to win any awards for best lighting, certainly. But it's, you know, getting to be something a little more usable. Right? I mean, that is lighting you could actually start to use, you know? And we haven't really taken into account the normal stuff yet either, so we have to kind of think about this a little bit more and work on our lighting computation as well. But, you know, we're getting there. And again, a lot of that problem just a lot of it tends to be like, how are we going to bin enough stuff into enough places to really get it going okay, right? But, you know, that's starting to be plausible to me, right? Like, I think we're starting to get somewhere. So if we had if we turn the crank a little bit on this one, start to get a little bit further down, maybe figure out, start to look at how we're computing our lighting, and maybe write some things into the voxels that tell us directional information. You know, I could see this being something that is not completely useless, right? Because, like, for example, if we knew the directional, the incidence direction here, we'd also know stuff about, like, this should not be lit down here, right? But right now it doesn't know that because it doesn't know what direction light's coming from. And furthermore, we can't differentiate between, like, these sort of siding pieces here, right? Not that we really care about underside lighting too much because we'll never see it, but I mean, you know, it could cause other problems. Like, well, you know, you'd have the same problem if you were on the other side, like over here, on a thin thing. In fact, you can sort of see that happening right now, right? See how that's lit? And we don't want that to be lit, right? So, but that, like I said, that's kind of getting there. Like, I feel like we're sort of getting a little bit closer now. We've got a way to kind of smear lighting out into the environment and produce something that, you know, we could potentially start to use game-wise. And that is a good thing, I think. Right now, it's a little too soft. And again, we don't know the direction from which the light hits the surfaces yet. And that creates a problem because without that piece of information, we don't actually have a way to compute what the lighting should be, how the lighting should attenuate based on surface angle. And we do want that as well. And the reason we want that, right, is so we could differentiate surfaces like here. So you can kind of see how this is all just really smooth, but there should have been a hard edge there because this is a hard edge. So the lighting should change on the surface a little bit more dramatically than it does. So that's another one. All right. All right. Stretch time. Okay. All right, so we've got a little bit of time left. So maybe I think what I might try to do is I think I will try to go put in a little bit of directional information there. I think that sounds like a good plan to me. So in other words, when we store these light things in here, we've got the color. I may try to store the direction as well. So what I'll do is I'll just say like, okay, you know, we send down the this light data with stuff, and I would like to also send down I'd like to also send down a light direction. I'm trying to think of what the best way to send that down would be. And if you look at this stuff, you can easily see how there's a lot of ways that we can make this smaller and more efficient as we would go forward, when and if we need to. So for example, if we do have that sort of lighting texel thing, you can see how the lighting texel that's sort of discussed there, it has a full floating point value for its position, but we probably don't need a full floating point value for its position because remember, it's confined to a particular voxel. We know that it's in a particular voxel. So we could just have that position be relative to the voxel corner, at which point we could probably store it at 16 bits per coordinate, maybe even 8 bits per coordinate, and be fine, because quantizing those values probably wouldn't matter, right? We don't need to know precisely where this lighting was computed. We can know like approximately where it's computed, and that would be fine. So, you know, we can imagine getting that down to like a U32 even, probably, for the position. And the same would probably be true for the direction. So I'm not going to do that right now, but it's just worth noting that we could do that. So if we needed to in the future, we could easily do something where we had more information here about what was going on in that respect, right? So what I'm going to try doing here is I'm going to say, let's go ahead and make a v4 like directional piece of information here. I don't know why I'm bothering to keep track of how big these things are. This is not 8 megabytes anymore. This is something. We don't know what it is. I mean, we know it's 8 times 8 times 8 times 2, so we actually do know what it is. I guess if we were keeping score, 8 times 8 times 8 times 2, it's 1024. So it's like hardly. Is that really? Is that really that small? So that's fine. And based on how few lighting samples we're taking, that makes sense, right? We don't need a voxel to be huge if we're only taking 4096 lighting samples at maximum. If we were able to increase that lighting sample number up to a higher number, that would probably argue for increasing the resolution of the voxel, because the only point, again, the voxel is pointless. We wouldn't use the voxel for any purpose if we didn't have to care about computation time. The voxel is purely there to make sure we don't spend a ton of time looking at lighting samples that are far away, right? That's the only reason it's there. So it only needs to do that. And in order to do that, effectively, it just needs to have a size proportional to the number of lights that are actually being computed, right? Right now, our lighting computation is not particularly good. That is some old water. I'm not drinking that. And so we don't really need the voxel to be particularly big. In the future, we're going to have to tune these a little bit more intelligently and, you know, figure out what we're doing with them. But for now, that's fine. All right, so there we go. That's our current situation. Let's see if we can fill out this D with something reasonable. If I was going to fill out this D with something reasonable, then what I would be able to do is stuff a value in here, where in addition to C sampler, we would have D sampler, like so. And, you know, If we wanted to, we could actually make the C value be, well, I don't know that we really could. Let's leave it at this. So anyway, if we have a D sampler in there, then when we actually look up the color value for the light, we can actually look up the direction value for the light. So here's the light D, like so. And once we look up that lighting value in there, we are able to use that as part of the attenuation or any other kind of value we would want. So once we have the contrib value based on the distance away from the lighting sample that we're taking, we could also add in something there where we multiply the contrib value by, the cosine, for example. Again, do we have the macros for that yet? We don't. We don't have any macros. All right. Anyway, where we have a cosine, so that we can take. Well, I guess we don't actually need cosine when I said that. This will produce the cosine for us. So we can take the inner product of the lighting direction, so we know where the light is incoming from, and whatever the world normal is. So that'll give us a cosine that'll tell us how coincident those two are, and as we get further away, the lighting will contribute less, right? So that's really all we need to do to get that working. That's really about it. So most of the work is going to be plumbing here, of getting that D value down to the system. So let's go ahead and take a look at the render group entry here. We just need some way of passing down whatever this is going to be. So we just need something that like passes down a pointer value to that D there. Yeah. Oops. Know where push lighting is. There it is. So really all we need to do here is just copy that pointer out. And that's going to be an F32 here, like so. And when we have those values in the OpenGL side of things, we just need a way of making sure that those get pushed through. I think that's all we have to do there. And then when we actually sort of set up the C sampler, where is it? There it is. When we actually submit these textures, yeah, we have to put lighting D in there. And this one's going to be, it's not going to be the same format, right? This one's going to be floats for now. And the internal storage format for it is, oh, I guess it's specified elsewhere. Oops. Yeah, so we've got these sort of hard-coded here. Active texture 2, 3, and 4. Which isn't fabulous. So we kind of just made those line up just out of whimsy there. That's alright. I mean, what could possibly go wrong? I'm sure it will be fine. Yeah. Anyway, let me actually go ahead and finish this, though. So when we bind this guy, this is going to be exactly the same code as this, only it's going to be float instead. So this is a floating point texture. Like I said, we probably don't really want to do that. You know, to be honest, we don't. Yeah, we really don't need to do these as floats at all, but for now we just are. So I feel like we don't want to introduce complexity of like figuring out quantization and stuff like this for no reason. So that's why I'm just at the moment leaving everything in its normal form without trying to smack anything down into a smaller space or quantize something. that we don't need to, just because as we're experimenting with lighting, I don't want to introduce additional things that could create bugs, which then we think are yielding improper results, or throw away some experiment because it doesn't work, when it turns out the only reason it doesn't work is because we had like a bug in how we were quantizing it or something like that. So that's the only reason I'm keeping something like this in floats. We absolutely don't need vec4s in here, and we probably won't, you know, in the final version ever store anything like that. But just, you know, keep that in mind. That's what's, you know, that's what's going on. Okay, so now that we've got that straightened out, I'm not sure that it's going to find those correctly. Let me look at how that was working. So if we take a look at lighting C, I guess it really just does depend on the order. So it just knew that it was going to be like, okay, texture sampler, depth sampler, pnex sampler, C sampler, D sampler, lookup sampler. Somehow it knew that these were where those were going to be. Which is kind of nuts. So here's the Z-bias program, right? And you can kind of see, you can see in here it's going to call use program begin, and that's going to go through here for each of these GL uniforms, and it's going to set the sampler index to be like 0, 1, 2, 3, 4, 5, 6, 7, right? So it literally sets them in that order that they showed up here, right? It's texture sampler, depth sampler, next sampler, C sampler, D sampler, lookup sampler. I mean, that's the order they're going to go in. So if I look up lighting C, where that's actually, lighting C, where that's actually getting bound in here, then it's texture sampler, depth sampler, pnex sampler, C sampler, and you know, hey, it does line up. So, you know, I guess that just works. All right. Implicit cast from vec4 to vec3. Sorry about that. I didn't mean to. That should be right in here. Okay. So now, at least in theory, we are taking into account the lighting direction. Everything will be black, as it was there, because even if we did everything right, we are not filling out that lighting direction with any information. So what we want to do now is we want to figure out a way, when we compute the lighting, to put something useful in there, right? So when we're packing this stuff down and we're setting this stuff up right here, you can see us doing this computation. You can see us computing the color value that we're going to have here. And you can see us sort of sticking that value into dest C. What we need to do here is stick some value into the directional component, right? Now, the problem with this is it's harder than it looks, because I don't think we track this information, so we're going to have to actually do some work to go in and put in tracking for this information, I believe. But in terms of like render elements here, I don't remember where we defined lighting elements, so I'm going to look. So here's the lighting elements. And what you can see from the lighting elements is that although they store their normal, they don't store any particular idea of what direction their incident light came from, right? And so the actual amount of color that they should be that they want to say is here, we're not really tracking that quite right yet. So we kind of have to go back into the lighting computation code, which is okay because that's code now that we actually have to start improving and probably turn into GPU side code. I'm guessing. I'm not sure because it depends on how we want to do this long term. But we need to do something with that code so that it runs in real time, or runs over a series of frames and gradually updates its results, or whatever else we're going to decide to do with it. But whatever we decide to do with it, we have to make it so that it outputs solutions every frame, rather than being something that you hit F1 to do, right? So if we're going to do that, we need to go look at how our lighting is being computed, and when our lighting is being computed, we need to sort of put that information in there. So let's, wait, that's not what I wanted. Let's go into render group here, where the lighting's getting computed, which is here. And we're skipping the ambient occlusion, right? That doesn't actually occur yet. And here's the compute lighting. So you can see what it does is it has some number of iterations. It goes through each of the elements. It casts out a bunch of rays to see what it can hit and retrieve. And then when it's done, it goes through each of the, well, I should say that this source index here is it going through those to see whether there's any shadowing. When it actually finds something that it hits, it goes ahead and accumulates the color value from whatever this particular one was, right? So let's take a look here. So here's the ray caster, right? It's going to cast some number of rays from wait, what is it going to do? This is very weird. How did we end up with this structured like this? This is the problem of having to have 2 or 3 months off, or however long it was with the Intel chip fiasco. So we're looping over each of our iterations, which makes sense. We're taking each destination so that we're going to update our lighting elements, right? We're taking a set of rays and initializing some directions we might cast, you know, off those rays. And then rather than looping over the rays, we decided to loop over the sources and then test whether the rays hit for that particular ray. It's just a strange way for me to have structured this. And I realized we were playing around with this code a bunch, so maybe I hadn't, you know, maybe we kind of backed into it, but it seems like you would loop over the rays first, and you would loop over the sources second, because otherwise you're computing the transference. Like, why are you computing all of this stuff if you're never going to use it? Right? You only do this. I mean, granted, the optimizer probably doesn't have any trouble figuring that out, because you can see that the only place that result is used is inside here. So there's no real problem with that. Like, it's not, you know, it's not awful or anything, but it's just strange. Like, I'm not sure why you would be doing it that way. I'm not sure why you do it that way, and I'm also not sure why you would store all the rays simultaneously like that, because if you just looped over the rays, then you don't care. You don't have to store them in a separate array, right? That is just some really strange stuff. That is just purely peculiar. I feel like we should reorganize that to be clear, because again, I just don't see any reason for it to look like that. It's very counterintuitive. And I realize that the reason for that is probably because we started with a sort of bidirectional radiance transfer kind of structure, which is dest, source, and squared. And then we added the ray check inside. So it makes sense, I guess, why it ended up this way based on how we did it. But just because we did it that way doesn't mean we should leave it that way. So it kind of feels like this should get unspun. I don't know if I want to do that right now, because we might want to wait till next weekend to start that, but that's probably something we should do. I'm going to put a little... So yeah, I think that's probably, because I don't see any benefit to doing it the way that we're doing it. It seems just purely, it seems like just purely more work. So I'm just going to assume that that was because of the way we happen to do it and that there's no good reason for it. Anyway, point being, when we actually do this summation and we're accumulating our results into a QMC, one of the things that we do, that we can tell about that, I suppose, at this point is, well, let me take a look at where QMC is even used. You know, is this even right? Because if this accumulator is getting, this doesn't even really make sense to me. So in order for the closest hit ray index stuff to work, you have to have checked all the sources first. But this looks like your accumulator, it looks like this would be order dependent, right? Like, yeah, this is just not right. I mean, that just does not make any sense to me whatsoever. So yeah, that really doesn't make any sense to me. So I think that's just kind of bogus and probably not something that we really want to use. Because you can see this closest hit ray index equals T-ray thing. We're accumulating a value, but we don't yet know what the closest hit value is going to be, right? So in order to know that this is the closest value, we have to have looped over all the sources first, right? And this would have to be a QMC equals result, not plus equals result, right? And we would need to store one result per array. Yeah, this is just kind of garbage. Like, I don't think that is at all sane. I'm pretty sure it's not sane. I'm just going to edit this now, because why not? So if we take a look at what's going on here, what I want to do is produce a piece of array information. So forget that. Like, that's done. That's over. So what we want to do here is we want to produce array direction. Right? We want array direction here. And we want to loop over a number of arrays. So how many arrays we're going to do, I don't know. Actually, you know what? I guess I shouldn't delete that quite before. Let me just see how many. We're doing 8 arrays. All right, so we're doing 8 arrays. And then here we've got array direction. And that's the array direction that we picked. All right. We've got a closest hit. Let's just keep 1 of our F32 max. And then we're going to do this nonsense here. Okay. So we computed our array direction. We don't need an accumulator because well, I mean, we do, but it's going to go outside, right? So for a particular array, we go through and we now test all the sources to see whatever the closest hit was, right? To camera looks like something that can be computed outside because it's not dependent on the array. So then we loop through all of our sources, and we really don't need anything but the light distance here. So this ref C, emit C stuff can go in here. So really all we're doing is checking to make sure the light is not on top of us, right? But assuming the light's not on top of us, then off we would go. We don't really need to do that yet, though, I don't think, because we can actually do this stuff now on the outside. So for each source ray, we would just go through and say, all right, we know what the ray source n is because whatever the ray direction is times source n, there it is. We can do this testing, all just works. And then if we eventually make it into the closest hit stuff here, where we know we've hit this particular source. Sorry, I don't know why I quite did what I just did there. I didn't mean to do that. I meant to do... that. So we loop through the source indices, and we just figure out which one the closest hit was, right? So we would just keep, instead of an array of these, we'd just keep 1, and we'd also keep like a, source hit, so on. So that figures out for this ray, who did we actually hit? And when we know who we actually hit, out here, if source hit is not equal to what we set it to at the beginning, so if we actually found a hit, then and only then would we come through and do this stuff. Right? So in the case where we actually have a valid hit, and we know it's the closest hit, then we would actually come through here and compute the lighting transfer between the two of them. Right? And then I think we're actually done. Is dest_accum_c ever set to anything? So as we come through here, yeah, this right here would be like a cum C plus equals total light, I guess. Right? So that's all the lighting contribution that comes in. And then when we're done with all that, and we've accumulated all of it across all of the rays for that destination, then it would get summed in. I think that's actually correct. Oops. So yeah, this too light here gets normalized eventually by the light distance. Do we actually use too light in here? No, we don't. So this is actually in here, and the only problem that we have is we got to make sure we don't test it against itself, because it will always be its own closest hit since it's right on top of itself, obviously. So in here we have to do a thing that's like if source index is not equal to dest index, right? So now that's reorganized to be more sane. Here we're taking however many rays we're doing, and we're sort of weighting by that. I guess we just need to have that be a constant. And off we go. Now, in order to see whether I just completely ruined all of our code or not, obviously we have to stop doing this because that will kill any... we are still not setting those D values, so that would immediately kill anything that we did. So hey, there we go. Now we've actually got our lighting back, and I think it's actually working more correctly now, perhaps. Although I don't actually know because I'm not sure. Like, it's kind of hard to tell without we don't really have good lighting testing code at the moment. We don't have like a Cornell box or something we can set up to see whether our lighting is getting better or worse when we make changes like that, but it looks roughly the same to me, and so we haven't destroyed it too much anyway. So that's the good news. All right, so now that we took care of that, how much time do we have left here? What's the status? 13:11. So we've got 4 minutes left. So we're not going to get very much done in 4 minutes, but that's okay. Let's go ahead and try to do this. So we've got our D value here, and what I'm going to do for our D value is I'm going to say that for these lighting elements, we really want to sort of start to converge on like a more sane structure for these lighting elements and figuring out what we're trying to actually say here. And so what I want to do is have some way of producing like, okay, for the lighting, we want two canonical values. There's like a, incident light and a, I think technically it's generally called a bent normal, but I don't really love that term, so I'm going to call it like average direction to light. And so the two values that we need is like an RGB value that's like, here is how the light is you know, kind of coming in incident to. Oh, did we just lose our net connection? Ooh. So I guess I'm talking to myself here. Looks like the net went down. I'm looking at it here, and all of my programs are basically on the left here saying, as of about 2 minutes ago, 3 minutes ago, everything is down. And that's not good. Yeah. Well, so sorry, there will apparently not be any Q&A, but the recording is still up, so the YouTube will have the correct video. So sorry for anyone who was watching the stream. It looks like network provider is has gone down. Anyway, so what I want here is I want a value that says here is how much light is incident on this location, and I want another value which is like if you had to tell me one general direction where the light was coming from. And, you know, obviously the light comes from many different directions, so it's not like you can really say definitively, here is where the light is coming from, because the light's coming from everywhere. But if you had to say one general direction where the lighting was coming from, where would that be? Something like that, right? And we probably want that average direction to light to be something that comes, that's going to be more sophisticated eventually and sort of give us a little bit more information about how we should attenuate the light based on facing direction, because that's really what we want. So if the lighting is coming sort of evenly from everywhere, we would maybe have a tuning value. And maybe that's what our fourth parameter is. But anyway, that's what we sort of need to get to, right? And that's what we'll talk about next week. And I'll just leave the lighting where it is today. Okay. So technically this is the Q&A. I can't take Q&A because as far as I can tell, all of the internet stuff is down. So I'll have to contact the internet provider to find out what happened. But you know, we will get to that at some point. Until then, yeah, I will just close the stream as normal. Thank you, everybody, for joining me for another episode of Handmade Hero. It's been a pleasure coding with you, as always. If you would like to follow along the series at home, you always can by pre-ordering the game on handmadehero.org. It comes with the source code, so you can play around with it. We also have a forum site you can go to if you want to ask questions. We have a Patreon page you can go to if you want to support the series. And we have a schedule bot that tells you when our episodes are going to be live if you want to catch them live. There's an episode guide that's down at the moment, so you can only get, it's not quite up to date yet. I don't know what's happening server-wise. I don't run that stuff, but hopefully that'll be back and functional again soon. But that's about it. I will be back here next weekend when we'll take a little closer look at the lighting. Until then, have fun programming, and I'll see everyone on the internet, assuming my internet connection comes back at some point. Take it easy, everybody.